My name is Derek Saltzman, and you're tuned in to the Climate Action Figures podcast.
Hello and welcome to Climate Action Figures, Tales from the Deep South, Part 2. My name is John Whidden, and this week on the program, you get to meet Derek. First, this week's QuickFix, which comes to us from an interview I heard with tech expert and analyst Carmi Levy. We have talked about AI on the program before, and more people are aware of the energy that AI uses, and Carmi gives us a really great reality check on this. What he did was he compared a Google search to the equivalent of a 60-watt light bulb, and he said it's about 17 seconds. Then he says, okay, if you use ChatGPT as an example of AI for the same prompt, same question you asked Google search, it takes about 10 times that amount of energy. So about 3 minutes with the same light bulb. And that's for each prompt. The interviewer asked what we can do to mitigate that. And Carmi said he named at least 3 things that we can do. First of all, ask yourself, do I need to use AI for this question? You know, if I'm asking the temperature outside, can I look at the thermostat instead? Second is minimize the extent of your ask. So cut to the chase. Don't get lazy and have a big conversation, because every prompt, every refinement takes another 3 minutes of the light bulb burning. So be succinct. And he added, interestingly, don't say thank you. He said, AI doesn't care whether we thank them, even though it seems polite to us. But again, there's another 3 minutes to have the thank you conversation, or maybe more. He also said we need measures, like a car will tell us the fuel efficiency. We need a tech efficiency tool. So very interesting commentary from Carmi on that. Welcome, Derek. And you're an engineer, so we'd love to hear what you think about that quick fix.
Yeah, no, I mean, I definitely agree with those points. Being an end user and a user of the AI and the chat GPTs of the world, I think having a good understanding of what you're prompting it and what you're truly seeking, and if you really need to use it, because he is correct, it is an energy hog. It consumes quite a lot of energy. If you were to tell me, hey, this query costed, 100 units of carbon compared to the other one costed 100,000 units of carbon, that may help you kind of determine if you want to go down that route and still query those questions. In the future, it'd be best to start pressuring these companies or organizations that are utilizing and building these large infrastructures for that, the AI development and AI race, that they look at energy systems and energy sources that are more fuel efficient. So you have a lot of data center companies that are looking at buying and building their own fusion reactors on site to generate their own clean energy, rather than tapping into the grid or tapping into a more fossil fuel based source. So I think with time and innovation, you'll start to see new developments in the world for energy when it comes to AI.
Right. And as you say, the consumer ultimately can put a lot of pressure, perhaps is the best positioned to put a lot of pressure on the companies to do their part. Now, you, Derek, are an aerospace engineer at the start. What took you in that direction to begin your career?
So I came from a background where when I was really young, most kids, their first interaction with aerospace is usually an Estes kit. They're small, maybe about 5-10 inch little rockets that you put a little motor into, and you 3, 2, 1, press the go button, and it, of course, will fire into the sky and a parachute comes out. That was my first interaction. I used to go and do that with my father when I was really, really young. And then
I spent so much time with my Estes rockets, you can't imagine.
yeah, I mean, it's the first area where you start to do engineering and failure analysis, and it's great. So from there, when I got into high school, we started to actually compete in rocketry. So we actually competed in competitions called TARC, Team American Rocketry Challenge. It was part of my high school at the time, and that's where I got the competitive edge. I've always played sports, so I was always very competitive with football, baseball, and it was pretty cool to take the competitive edge to more of the engineering side now. So you got to use your brain, and it was all about who could build and design the best rocket to hit a specific altitude target and do a specific job. So that got my feet really, really wet about engineering, building, designing. I got to work with a professor known as Joe Vallone from Plantation High. He was probably my best professor and mentor as I grew up when it came to the field of engineering. So much so by our senior year of high school, I mean, we were doing projects with NASA. We were working on something called SLI, which stood for Student Launch Initiative, where we were building a full-on 8-foot rocket with a super powerful M motor. So, I mean, these things were going a mile high, carrying a pretty intense payload, and you would go through every engineering discipline of the preliminary design, the critical design review, the final report. It was just a really good point in life where it taught you a lot about the early facets of engineering before you hit the collegiate scene. And then when I got to college, I felt very prepared for what basically the engineering career had to offer.
Now, let's just place you geographically, because I introduced things by saying this is Tales from the Deep South Part 2. That's because you are connected with Sam, who was our guest a few weeks back.
Mm-hmm.
Do you want to just tell us about that connection?
His business, and we were working on our business at the time, and we were both engineers and material engineers or chemists. And they went down the path of agricultural tech, and we went down the path of the material tech. But Sam and I have known him for quite a while. He's a great friend and really great business operator from what I can see. Yeah, no, Sam and I have known each other for quite a while. We come from the same university. Our alma mater is UCF. I think he's a bioengineer or a biochemist by trade. I'm a material engineer by trade. We work together closely. We cross paths in the UCF's Blackstone Launchpad, which is basically the UCF startup incubator, where he was working on.
And you are still in Florida, right?
Yeah, still located in Orlando, Florida.
So back to your story, Derek, there was a competition that you won for business. Is that correct?
Yes. So our freshman year of college, we were doing a bunch of engineering competitions because we were freshman engineers with a lot of experience, my co-founder and I, Mason. Funny enough, he was my first roommate that we ever met. So our first roommate, he came from background in planes. I came from background in rockets. So we hit it off really well. Did a bunch of engineering projects together, and we walked by that same incubator lab that I was mentioning, the Blackstone Launchpad, and it basically said a competition, win $75,000 if you start a business. And we thought, I mean, we're engineers. How hard is it to build a business? You quickly realize it's very difficult to build a business. But that was our bug. So we walked in there, got meeting with some coaches, and they said, hey, there's a business competition. Try to figure out how to start a business. So we said, all right. And that was what kicked off our very first business of basically, we were aero engineers. We built a drone. We attached some sensors to it. We would fly it around farmers' fields to try to give them some vegetative, basic data on their farm and tell them, hey, this is what's going on with your farm. You need more nitrogen or you need more water in this area. And you quickly realize through customer discovery what works and doesn't work. And it took us a little bit of time, but early on we were able to find that may not be the best route for us starting off as a business. These are guys that are managing 200 plus acre farms for soybean, corn, sod, whatever it may be. And we just realized that we're trying to sell this advanced, not only they're not going to fly the drone, they're not going to be able to understand the data digestion part of it. So we, as young engineers, realized that's more of a data science problem. We weren't data scientists. We were more aero engineers or more mechanical hardware guys. So we decided to pivot the business actually into a different direction where we focused mainly on that, where we started focusing on the materials development of the drones, which led us down into basically making carbon fiber or carbon fiber fabrics for the racing drone world.
Okay, so racing, many of us don't know about the racing drone world. Tell us a little bit about that and why the carbon fiber is such an important aspect.
Yeah, so I'd say about 6 or 7 years ago now, it was first shown on ESPN's Drone Racing League, or DRL was the really big league at the time. But they were essentially the group that were putting on these really high-end events where you would have pilots that were put on the full-on Ready Player One virtual reality goggles, so you're sitting in the cockpit of the drone. And you have these drones that are flying around 80 miles an hour doing acrobatic flips, turns, loops. And you can imagine it's almost like you're sitting in the cockpit because you have the goggles on and you're seeing from the perspective of the drone. Now, all of these drones are made of carbon fiber, which is an extremely lightweight, strong material. And the main reason for that is to keep them fast, keep them in the air. And we saw a space in the market where we said, hey, a lot of these drones are manufactured with carbon fiber, and we are really good at composite or carbon fiber manufacturing from our first startup when we were trying to manufacture the drone for the farmers. What if we decided to actually manufacture the drones for drone racers instead? And that was a much more lucrative initial business for us, where we were able to basically work with a variety of distributors, as well as pilots. It was an up-and-coming space where we were able to manufacture custom drones for these guys. So we were manufacturing custom carbon fiber plates at different thicknesses, different sizes. And even if you look at the photo that's popping up here, The photo that you're seeing now is of a drone that's about 1 meter. So these are considered X-class racing drones. So they're about 1 meter in diameter from tip to tip. It's quite a large drone. So you can imagine about 6 or 7 of those flying around 80 miles an hour. They crash into each other. It's like NASCAR in the sky. So we saw that as potentially going to be one of the future sports.
So has drone racing continued to ramp up? Is this still a huge thing?
Not as big as it was on ESPN, but they've gotten even larger now. So you have a company actually based in Australia called Airspeed, where they're actually putting humans inside of the drones now. So no more is it the 1 meter long drone. Now you're having drones that are the size of cars, and they're putting people inside them and they're flying them like the Red Bull races.
Okay, we've talked about carbon fiber here, and clearly the weight and the strength are important aspects, but there are, I'm assuming, hundreds, if not thousands of companies that are working in that direction, but you've kind of taken it at a different angle, have you not?
Yeah. So as we were moving into the world of material science and engineering, my partner and I, Mason, we decided to go into the world of academia. So we started to work in the actual carbon fiber composites research laboratory at UCF, where essentially we were working on nanomaterial processing. So these are nanomaterials, or materials that are about 10,000 times thinner than a human hair. So super, super tiny materials, and incorporating those into carbon fiber to make them stronger, lighter, and more robust. We've come out with a nano coating. So we essentially have developed a process that allows us to take biomass, such as hemp and seaweed, which are raw biodegradable biomasses that exist in abundance on the planet, have a proprietary processing method that allows us to extract out a specific material from those biomasses called cellulose. Cellulose is the most abundant biopolymer on the planet. It's found in every tree, every plant. It's pretty much the rebar that's inside a plant cell wall. So if you've heard the mitochondria as the powerhouse of the cell, well, cellulose is the rebar inside of the cell wall. It's quite analogous to that. And our process allows us to extract that and turn it into something called nanocellulose. Think of tiny, tiny little fibers that are about 10,000 times thinner than a human hair and 8 times the strength of steel per weight. So insanely strong, super tiny little fibers that nature has developed. So we took that biomimicry approach, and we decided to take that and put those tiny fibers on the surface of the carbon fiber fabrics, essentially adding a nanoscale Velcro to the surface of the carbon fiber. And why did we do that? Or the entire reason of doing that is composites, or carbon fiber, is essentially layers of fabric. So it's fabric layers stacked together with glue. So it's what people in the industry call rags and glue. The biggest issue is the reason that they break because the fabrics, or the carbon fiber fabric, and the glue, that surface or interface breaks. So once you get to a specific amount of force or energy, it starts to delaminate and rip apart. Essentially, with our nanocellulose nano coating onto the surface of the carbon fiber, we increase that strength, or that bonding, or that adhesion between the carbon fiber and the resin, which allows you to make parts that are stronger, lighter, more cost effective, and overall just a better, stronger, cheaper part. And we're really excited about that because since we're able to put this nano coating on the surface of carbon fiber so high in the manufacturing process that it can have end benefits to a variety of different end customers or end markets. And these are people that are making, let's say, carbon fiber golf clubs, carbon fiber surfboards, all the way to aerospace grade planes, where you're trying to make a plane more energy efficient, or even for the future of aviation, where everyone is looking at new VTOL drones for point-to-point travel. We're able to make those vehicles lighter and even stronger. Even today, we're working with electric vehicle companies where the main goal that they have is reducing the overall weight of the vehicle so that the battery can work less and essentially push the vehicle further. So if we're able to reduce the weight of a vehicle by almost 20-30%, you can think those energy savings are then gained for the user. So you can now potentially have people that were originally afraid of buying an EV because of range anxiety. Now that anxiety may be reduced with the use of seaweed or hemp-based nanomaterials, which we think is a pretty cool future.
We won't ask the chef to share his recipe, but what is the critical component that is different than everything else you've seen before?
The main thing that we say, which is the big critical difference, is what we call in material science is chemical functionalization. Functionalization, all that really boils down to is, let's just say you're adding specific molecules to the surface of something so it talks to something else much better. Usually, if you don't have that molecule on the surface to talk to something else, then it's not going to want to do the dance. It's not going to want to bond. It's not going to want to glue. So the thing that we really focused in on is being able to have a clean, non-toxic process. Majority of the times, the industry uses pretty mean chemicals like sulfuric acid and harsh chemicals to do these processes. We developed a unique green chemical or green chemistry method that allows us to do this without having to use any of those toxic chemistries. And two, it also allows us to increase the efficiency of that chemical functionalization or adding that specific molecule to the surface, i.e., that's really where a lot of our IP is generated, where we're able to take this green chemistry functionalization process and turn it into what used to be seaweed now into this nanocellulosic goop. And once it goes into the carbon fiber, we've basically surface modified, or again, we've added these specific molecules to the surface of that nanocellulose so that it talks to the carbon fiber a lot better, i.e., just making a stronger bond, making a better connection, and making an overall better part when it's manufactured.
Now, we talked with Sam about greenwashing, and I'll have to ask you the same question because it sounds to me like your product is much more green than the average product in this class. Tell us about what you see out there in your field in terms of greenwashing and how your product is different than that.
Oh yeah, I mean, when you're in the industry for long enough, there's usually always an outward narrative that you hear from big companies, where they want to be more sustainable, they want to be more green, and then when you get behind the curtain, or you start actually having conversations, everything boils down to the bottom line, or how is it going to affect the financials? How is it going to affect the bottom line? So yes, greenwashing is a pretty strong, adamant thing that's been happening in the industry. We've seen it ourselves in the textile space, where people describe something as, let's say, vegan leather. Everyone's like, oh my God, it's great, it's vegan leather. But when you actually peel back the onion, you realize, well, vegan leather just means plastic leather. It doesn't mean that it was made with cactus or anything like that. It's probably 2% cactus and 98% plastic. And that's just the overall aspect of greenwashing.
But the big difference with your product is that at the root, it is a natural product that you're using, seaweed, right?
100%. So at the root, we make sure we use actual biomass. So we're taking biomass that is coming from the beaches. So sargassum that's washing up on the beaches of the Caribbean, of Texas, of Mexico, as well as stuff that's even harvested and grown in the North Atlantic. So these are actually giving what used to be lobster farmers and crabbers, now on their off season, they're growing seaweed, and it's a whole new revenue stream for them to farm seaweed. And we're taking that raw biomass again, and we're not using any of the harsh or toxic chemistries that are used today. We do everything with pretty much materials that were extracted out of fruits and grains. So like for instance, citric acid, things that you come from like orange peels and orange juice. We use those types of chemistries to impart all our chemical functional groups.
Now, a lot of business people, Derek, you'll know, don't really give much thought to environmental impact. More and more these days, hopefully they are. But what makes you so interested in developing great products, but also taking care of the environment at the same time?
I think it's quite interesting. I think at the end of the day, nature does it best. We are always trying to mimic nature to make a project or make a product. For instance, I mean, we looked at birds flew amazingly, and then we decided to build the plane. Nature didn't decide to strap engines to something, blow it up with some compressed gases and chemicals and shoot it out the back. They developed a whole different system for a bird to fly naturally. So I think as engineers, we're always striving to try to reach that. And when we say nature does it best, it truly does. So not only do we see that taking care of the planet is not only a great thing, utilizing these greener chemistries, but they're actually more efficient and they can beat out the synthetic materials that are used today. It's just that we kind of forgot our way. More natural materials were used in the early 1900s. You can look at Henry Ford. They made hemp door panels. They were looking at these types of materials. But then you had the age of the petroleum industry and plastics kick off, and finances became the main driving force as we industrialized. And we're just now getting back full cycle, realizing like, oh, the actual natural materials could work better than what we pretty much have engineered for the past 70 plus years.
And as you develop seaweed, for example, I think to salmon farming. We thought, oh, that's great. Well, I'll get all our salmon from farms, and then we won't have to take the salmon out of the natural environment as much. And then all of a sudden we find out there's all these problems with lice and other issues with salmon farming. Are there similar problems with using farming seaweed for this product?
Entirely no. So some of the seaweeds that we work with are actually invasive seaweeds. So sargassum is a really big issue. So we're actually helping out coastal communities because essentially sea levels have gotten hotter, and as they've gotten hotter, it causes more algae blooms. So now you can actually look at something. It's from a satellite. You can see it from satellites. You can look at the large sargassum bloom that happens every year, and it's basically a giant mass of seaweed that starts in the Atlantic Ocean and migrates its way over into the Caribbean and slams into the U.S. coastal regions and becomes a really big issue for tourism, for local economies. It starts to degrade and cause putrid air, which is really, really bad. So not only are we working with invasive species, we are working with farm species. The great thing about the farm species is they actually promote biodiversity. So when you're actually growing these seaweed farms, you're actually incentivizing coral, you're incentivizing other organisms to actually grow onto the seaweed and bring biodiversity to the region. And since these are cyclical processes, which happen every, like say, 6 to 12 months, once you remove it, you have another batch in the water. So you're continually growing more biodiversity as you scale. And seaweed is a fast growing plant. It's not like trees where it's going to take 100 years. It's similar to a grass where it'll grow in a few months. And that's why a lot of the nutrition, a lot of the diet of Southeast Asian countries are based on seaweed, because it's a fast-growing, high nutrient-dense material or plant to eat. But we don't see any adverse effects as of yet of growing seaweed at scale. Actually, we see some benefits, realistically.
When you look ahead 5-10 years, where do you see yourself and this company?
I 100% we see ourselves. Hopefully, we'll be making electric vehicles and some of the new electric planes and aviation space a little bit lighter and a little bit more fuel efficient. That's our end goal. But not only that, seaweed has been shown. We have a couple researchers that are actually buying our materials for tissue engineering. And it's not an expertise of ours, but I mean, within the next 10 years, you may see organs being built, a new heart, a new liver, a new pancreas being developed with, funny enough, seaweed extracted from cellulose, where they're using it as a scaffolding material to dope it with specific stem cells or retina cells to grow an organ. So who knows, maybe in the future you could, for all the people that are, let's say, on dialysis or on those types of machines or have those health issues, they could come in one day, get a scrub of their own stem cells, and then within a matter of a couple months, they could have a new pancreas or new kidney grown for them on potentially seaweed.
Wow. Big dreams. Congratulations on all your success with your business so far. And before we let you go, we definitely have to ask you what your climate action is.
So for us, the biggest thing that we're looking at is reducing or increasing the amount of biomass that we utilize. Seaweed sucks up about 1 to 2 kilograms for every kilogram of biomass. So the more and more seaweed that we use and grow, the more and more CO2 that we're sucking out the atmosphere and putting into products, whether it be into cosmetics, composites, or even tissue engineering. So our whole goal is to reduce around 700,000 tons of CO2 over the lifespan of our business.
Wow. Big climate action today. And last question for you, Derek. What gives you hope?
I'd say the younger generation. I would say seeing some of the younger engineers and some of the younger people really care about trying to develop a more sustainable future. Not only are they worried about world issues, but they're also thinking about how we're going to solve those issues in an effective, more green manner. I think with the advent of AI and new technologies, I think we'll be able to actually crack the nut of being able to generate energy more efficiently and have more efficient processes that allow us to just thrive better as a society.
Well, thank you so much for taking time out of your busy day to join us, Derek.
Thank you. It was an absolute pleasure.
And thank you, dear listener. Oh, also, thanks to Sam for connecting us with Derek. Listener, we love to hear from you, so please let us know what you think of what you hear and see on Climate Action Figures. You can connect via comment in YouTube, send us an email, or send us a message on Instagram. We will be back again next week, same time, same place, to hear from another Climate Action Figure. Until then,
go figures.
This has been Climate Action Figures. Our show is produced and hosted by John Whidden. Our creative consultant is Kayla McIntosh. Our theme song is Hawaii Vacation by Tovari. You can find us on Instagram, Facebook, and YouTube at Climate Action Figures. That's all one word. And if you have any other questions or comments that arose from this or any episode, feel free to reach out to us at climateactionfigures@gmail.com. And thank you for listening. We'll be back next week with another Climate Action Figure.